This is Neil from Anabit, and in this video, we're going to be talking about the highest measurement accuracy and resolution IoT or AIoT platform available on the market today, and that's Anabit's AIoT Precision Logger. Before I get started, I'll just mention, please check out anabit.co, where you can find open source data converter products. We also have a lot of tutorials, both blog posts and videos related to data converters. If you're interested in that stuff, please sign up for our newsletter. You can get updates on that whenever we come out with new content and, of course, new products. Check us out on Instagram, and let's dive into the AIoT Precision Logger. So here's what I plan to cover in this video. We're going to first do an overview of the different features and capabilities of the AIoT Precision Logger and what makes it such an high accuracy, high resolution measurement platform. Then we're going to look at a demo of it in action, an IoT demo. So we're going to use Wi-Fi to connect it to the cloud. We're going to use Arduino's cloud platform, and we're going to send precision measurement data to the cloud and view it on our browser. Then we're also going to look at the code I put together to do that. And of course, all that material or code will be available for download. And then from there, I'll just provide a quick overview of where you can find more information on the AIoT Precision Logger. Okay, we are zoomed into the AIoT Precision Logger, and two of the main parts on this board are first the ESP32S3 module. So the S3, what's great about the S3 is it's a very powerful computing platform, and it has basically capabilities for doing calculations related to neural networks. So that's where the AI capability comes in. Also, the S3 is compatible with the ESP Claw, which is an edge AI agent framework, which I'll have a link for in the video description. I plan to have a video on that in a future Anabit video. Here we have a ADC from TI. This is a 32-bit high accuracy ADC. It has a mux, so it can make multiple channel measurements. It has a programmable gain amp built in. It has the 32-bit ADC, as I already said. It also has built-in precision current sources, 2 of them. So that way, if you want to measure resistances or resistance sensors like RTDs or strain gauges, you don't need any additional hardware. You can do it with just this board. We have 11 different measurement channels. So you'll see 12 different screw terminals here. One of them is ground. The other 11 are measurement channels that route to the ADC's mux. And so the reason we have 11 is because we can do 10 single-edge measurements. So 10 of the channels used for the measurement, the other one tied to ground. And then we can also configure it for 5 differential measurements, and you can pair the channels however you want. The design is powered by 5 volts, so you can power it from the USB-C connector. You can also power it from some of these pins down here. The USB-C connector also allows you to program the ESP32 with just a USB cable, and you can do UART communication with the ESP32. We have one of the quick connectors. This was invented by SparkFun. So this provides I2C, 3.3 volts, and ground. So you can integrate sensors from other makers, actuators, things like that, all without doing any soldering. We have an RGB LED on board, which we'll see in the demo. And then we have a lot of design effort into the power system. So this ADC can make bipolar measurements. So plus 2.5 volts to negative 2.5 volts. And so we create a negative bus from the input of the 5 volts. We also have a lot of filtering on these power rails. So by the time our power supply voltages get to the ADC and the programmable gain amp, they're very low noise. So we do not affect the accuracy or the resolution of our measurements. Also on our measurement channels, we have a lot of RC filters for filtering out high frequency content, both from single-ended measurements and differential measurements from anything you connect to the board. The ADC has a built-in 2.5 volt high stability voltage reference for the ADC, but we offer an optional second external reference right here that's even higher accuracy, but it's 2.048 volts, and it's even higher stability over temperature changes. Now, once again, that's optional, and if you get that, it'll come with this dip switch where you can route the external reference to the ADC, or you can disconnect it if you want. Finally, we have various pins so you can access the different connections to the ESP32 pins. We also give access to the 3.3 volt bus and things like that. Okay, that's a quick overview. Now let's talk about our demo. You can see the AIoT Precision Logger here, and we're going to do a cloud demo. So in this setup, we have our ESP32 connected to my Wi-Fi network, and it's going to be grabbing measurement data from the ADC, sending it to the Arduino cloud, and we'll look at that data on a dashboard. And then, of course, we'll review the code. We're powering it from the USB-C connector. What you see here is the RGB LED, which will cycle through different colors. And I wanted to show the versatility of this design. So we're showing two measurements, a K-type thermocouple measurement and a current measurement. So you can see those are connected to the screw terminals. Right here, what I want to show is I have a sense or shunt resistor that's 0.1 ohms that we're going to use for the current measurements. So the idea is we put current through this precision shunt, we measure the voltage drop, we use Ohm's law to get the current value. And so what the AIoT precision logger board has is two blank pads on two of the differential channels, right? So these don't come populated, but they're 1206 in size, and it allows you to put a shunt resistor or even possibly a precision resistor for ratiometric measurements. So once again, very flexible measurement setups, whether you're doing straight voltage, current, or resistance. And then also you might notice, to make things interesting, we have two mugs of water. So I just put the probe inside the ice water. Next, we'll put it in the hot water so we can actually see some temperature action as we do the demo. So let's jump to the cloud dashboard. Okay, now we're looking at our cloud dashboard, which is capturing measurement data from the AIoT precision logger, pushing it through the cloud, and now we can view this anywhere where we have access to the internet. So I basically have a simple setup where I'm showing some of our different measurements. Now we're doing actually 3 different measurements, because if you're familiar with thermocouples, we need a cold junction measurement. And luckily, the ADC has a built-in internal temperature sensor, so we can do that cold junction measurement without adding any additional hardware. If you're not familiar with thermocouple measurements, I have a tutorial on that related to our precision logger, which will also work with the AIoT precision logger. I'll provide a link to that in case you want any more information. But what I want you to notice is we see the thermocouple temperatures very low. So basically, we're making a voltage measurement on the thermocouple wire, and then we're also measuring the internal temperature to do a calculation to get the thermocouple measurement. So we're looking at here in degrees C, and we're looking at here in degrees F. But what I want you to pay attention to is look at this voltage measurement. So for the thermocouple, we're measuring negative microamps of voltage. And that's because we have a low temperature. Once we do the high temperature, this voltage will shift to the positive region. But the idea is look at the type of resolution and accuracy we're getting to make this temperature measurement. And then I also have a current measurement set up. So I have the current measurement set up for about 500 milliamps over that current shunt that you're seeing. So let's do some interesting stuff. Let's change some things. Let's lower the current measurement, and then let's also put the thermocouple sensor into some hot water. Okay, first what I want you to pay attention to is the thermocouple voltage, because now it's going to go up, and you can see it now jumped, crossed the 0 volt line, and now we're at hundreds of microvolts, but positive this time. And now we're jumped up above 140 degrees Fahrenheit, over 65 degrees Celsius. And then another thing I did is I lowered the current value. So now our current source is doing about 1 milliamp. So great dynamic current range, great low-level voltage, high resolution capturing small changes, right? So that's the power of the most accurate IoT or AIoT measurement platform. Now let's take a look at the code and how we set up this dashboard. And of course, the code will be available for download. Okay, here's our main sketch. But before we go there, let's go to this data section on Arduino IoT Cloud. So I'm not going to go in detail how to set up a cloud dashboard and the things and the device. There's a lot of tutorials. Just go to Arduino Cloud and you can get started there. But what I want to show you is I create these variables in the interface, and this is what interacts between the code and what's sent to the cloud to our dashboard. So we have our current measurement, our temperature in Fahrenheit. The PCB temperature is our cold reference temperature. And then we also have our thermocouple voltage, right? And then, of course, we have the AIoT precision logger connected. That's online. It's on my network. So that's a little bit behind of how things are set up. It's really easy. And the dashboard that we looked at is just drag and drop. So very easy to set up. Check it out. There's lots of tutorials on that. Now we're going to dig more into the sketch or the code that I'll have available for download. Okay, here's our main sketch. If I go here, we can see a file called thingproperties.h. This file is generated automatically by the Arduino Cloud based on some of the settings we do in the user interface, right? So that's automatically generated. Then I included a local library from one of my other tutorials that we're going to use, that's used to do the calculations for the K-type thermocouple temperature. And that library uses polynomial values by NIST, the National Institute of Standard Technology in the US, for making sure you're doing standard, accurate thermocouple measurements. And I do have a tutorial on that if you're interested. I'll provide a link in the video description. This is the library for the ADC. This is the library for the RGB LED. Now, the RGB LED library is a built-in library to Arduino, so you can access it directly from the cloud. This ADC library is not available in the Arduino environment by default, so I downloaded it from GitHub and it was easy to import it into the cloud. So I'll provide a link to that library as well. Here I have some constants. For instance, the ADC is bipolar, so it's 32-bit. One of the bits is used for sine, so we have 31-bit number here. I have my two voltage references. For the demo, I just used the standard internal voltage reference, but we also have the optional higher accuracy external voltage reference. I have various different settings. These are related to the LED colors, which I'm using the Anabit blue, yellow, and pink. I declare some variables. These timing variables are all the measurement delay time it takes to complete one of the measurements. And like I said, we have three different measurements, right? We have the thermocouple voltage measurement. We have the internal voltage measurement of the internal temperature sensor. And then we have the current measurement, or really a voltage measurement across a current shunt to get a current value. Then what I do is I use these structures. I create this structure called precision logger settings. So this will hold a lot of the settings for configuring the ADC and the MUX and the programmable gain amp. So you can see, first of all, I'm defining the pins here. The sample rate, I'm going for the slowest sample rate. It can go up to about 38,000 samples per second. I'm using a basic filter, the Sync 1 filter. And then I have a gain of 32 for the PGA, the programmable gain amp. I'm going to use the internal reference. And then there's some other settings like chop, which reduces offset error. I have that off right now just to speed up the measurements, and some other settings. Then I do two more structures for my other two measurements. So this first one is for the internal temperature sensor. That's why it says temp here. You can see a lot of the other settings there. And then for the current shunt. So here I have a gain of 8, and I'm on two different pins than the thermocouple measurement. I then have functions to calculate the conversion time. That's the time it takes for each measurement to complete. I have some serial communication. I'm starting my ADC library with my chip select pin, which I'm using pin 10, which is the pin that's hardwired to the ADC chip select. These functions, properties, Arduino Cloud, debug messages, these are all automatically generated by the Arduino Cloud. And then the Arduino Cloud update is automatically generated as well. And then here in the loop, I'm doing the measurements. So I send in my configuration, which is my structure. I have to discard the first reading. Whenever you change settings on the MUX and the ADC, you need to throw out the first reading. So I take a reading and just do nothing with it. I delay for the conversion time, and then I grab this reading. So this is for the thermocouple. I get the code, I convert it to a voltage, I adjust for the gain setting of the amplifier, and then I basically do the internal temperature sensor reading. And then finally, as I get down here, I'm converting both of those readings into a thermocouple temperature, calling my local library. That'll be included in the files if you want to download them. I check to make sure the reading's valid. Then next, I do a current measurement. So once again, we set up the configuration, we discard the first reading, then we grab a voltage and we convert it to current. And then we're cycling through the three different LED colors every loop. And then I have various functions here that I have a lot of comments on that you can check out yourself. But, converting the internal voltage to temperature, this was defined in the data sheet, Celsius to Fahrenheit, discarding the first reading, converting the voltage, compensating for the gain amplifier setting, calculating current, so on and so forth. I'll let you check those out in more detail. Then I just want to conclude this video showing you the getting started page with Anabit's AIoT Precision Logger. So a lot of detailed information on how to get started. Here is the link to the ADC library, for instance. I also have a link here for a getting started sketch that doesn't involve the Arduino cloud. And in fact, it just sends data over Bluetooth. So that's another example you can leverage right here. I go in detail on the functionalities and the pins, all kinds of things like that. And then I have various other videos and things like that that you can check out to help you get started with the IoT Precision Logger. And of course, if you go to Anabit's product section, our analog to digital converter products, you can find the AIoT Precision Logger if you're interested in purchasing it. All right, I'm really interested to hear what you guys think about this. If you have any questions on it, opinions, did we do a good job? Did we miss anything? Please use the comment section. Thank you for watching.